You've driven past a tanker truck 1,000 times, big silver barrel on wheels, rumbling down the highway, and you've never once thought about it. But here's the thing, that truck might be the reason you made it home today. Why is it split into sections instead of one big tank? Isn't a single giant container simpler and cheaper? What happens if you skip the dividers? Is this about the cargo, the truck, or something else entirely? When the answer is a physics problem that engineers figured out the hard way, and it starts with something you already know. A tanker truck is basically a rolling container built to move liquid in big quantities: fuel, milk, chemicals, juice, even wine. But unlike a water bottle or a barrel, the inside isn't one hollow space. It's cut into separate sealed sections called compartments. Most fuel tankers have between 3 and 6 of them. Some have more. Each one is sealed off from the others, with its own valve, its own loading hatch, and its own vent. And here's where it gets interesting right away. Each compartment can carry a completely different product at the same time. One truck, multiple products, zero mixing. But that convenience isn't even close to the main reason they exist. Most people assume the compartments are there to carry more stuff, or to keep things organized like drawers in a cabinet. That's the intuitive answer, and it's wrong. The real reason isn't about storage at all. It's about physics. Specifically, it's about what happens when you put thousands of gallons of liquid into a fast-moving vehicle and try to keep that vehicle pointed in a straight line. Here's the thing about liquid in motion. It doesn't stay still. It shifts. It sloshes. It builds momentum. And a tank that's only half full is one of the most dangerous cargo setups on any road in the world. This is called liquid surge. And it's exactly what it sounds like. The liquid builds up force inside the tank, then slams hard to one side when the truck turns or brakes. That force doesn't just move the cargo, it moves the truck, and not in the direction the driver intended. This is the part everyone misses. Think about holding a full glass of water. Solid, predictable, easy to carry without spilling. Now think about a glass that's only half full. You tilt it, and the water rushes immediately to one side, shifts your grip, but throws off your balance. You felt that. Everyone has. Now, scale it up by a factor you can barely imagine. 5,000 gallons of diesel fuel. That's roughly the weight of 3 compact cars, all liquid, all moving as one connected mass, traveling at highway speed inside a metal shell. The truck hits a curve. The fuel surges toward the outside of the turn. The center of gravity shifts dramatically. The whole vehicle starts to follow the liquid instead of the road. That's how a 40-ton truck rolls over on a perfectly dry highway with no mechanical failure, no blown tire, and no driver error. The liquid did it. The liquid steered. But compartments change the math completely. Smaller chambers mean smaller amounts of liquid per section. Smaller amounts mean less total momentum when they surge. A wave that might have been 10 feet long inside one giant tank is now 2 feet long inside a smaller compartment. Therefore, the driver feels a manageable shift instead of a violent vehicle-controlling lurch. The truck handles more like a solid load, like a truck carrying gravel or steel beams, rather than a truck chasing a moving mass inside itself. Compartments don't just hold the fuel, they tame it. They break one enormous, dangerous physics problem into 5 or 6 smaller ones that the truck's suspension and the driver's hands can actually deal with. Now here's where it gets crazy. Because not every liquid vehicle uses this same approach, and the reason why tells you a lot. Train tanker cars, for example, are often single-chamber, one big hollow shell, same enormous load. But trains run on fixed rails with curves that are carefully engineered into the track at specific angles. The train physically cannot swerve, therefore surge hits differently. It rocks the car side to side, but it can't throw the vehicle off its path the way it can a truck. The road is the dangerous variable. Rails remove that variable entirely. Trucks can't remove it, so they had to solve the problem a different way. Milk tankers are a completely different story, and they're worth understanding separately. They use compartments too, but for a totally different reason. Not surge control, but product separation. A milk truck on a rural morning route might pick up loads from 5 or 6 different farms in one long trip. Each farm's milk goes into its own sealed compartment. They cannot mix. Each batch needs its own testing, its own traceability, its own grade certification before it gets to the processing plant. If 2 farms' milk mixed in transit, neither batch could be properly verified. The compartments on a milk truck are there to protect identity, not to fight physics. Same basic design as a fuel tanker, completely different job. And here's the rewatch moment. A fuel tanker can carry regular gasoline, premium gasoline, mid-grade, and diesel in 4 separate compartments on one single trip, and those 4 products will never touch each other. Not a drop, not a molecule. One truck, one trip, 4 products, 4 sealed rooms. So when you pull into a gas station and choose between regular and premium, both of those grades almost certainly arrived on the same truck. They just rode in different compartments, unloaded into different underground tanks, and came out of different pumps. And you never would have guessed. The compartment wasn't always part of the design. Go back to the late 1800s and the first petroleum haulers were wooden barrels strapped to horse-drawn wagons. One load, one container, full risk, no backup plan. When the first metal tank trucks started appearing around 1905 to 1910, they were single-chamber, one long hollow tube welded onto a chassis. Cheaper to build, simpler to load, and genuinely, repeatedly dangerous on real roads. Gravel surfaces, on sharp rural turns, no guardrails, no highway infrastructure. Single-chamber tanks were rolling the dice every trip. They rolled over on curves, they spilled on hills, they caught fire after collisions. Drivers died, cargo was lost, communities dealt with spills that contaminated roads and waterways. The crashes kept happening, and 2 groups started paying close attention: engineers and insurance companies. Engineers asked what could be done mechanically, and insurers asked what was costing them money. Both arrived at the same answer: break the load into smaller pieces. Not smaller trucks, smaller sections inside the same truck. The idea spread slowly through the transport industry, then faster as accident data piled up and regulations followed. By the mid-20th century, multi-compartment tankers were standard practice across the United States and Europe, not because a single inventor had a brilliant moment, but because the road kept teaching the same painful lesson until the industry finally built the answer into the metal. One theory that historians of transport find interesting: dairy haulers may have accelerated this shift for fuel transport. Milk haulers were already compartmentalizing by the early 1900s, not for safety, but for product integrity. The idea that a metal wall inside a tank could serve a purpose beyond just holding liquid was already proven and trusted in dairy. That thinking crossed over. The same logic that kept one farm's milk from blending with another's ended up keeping diesel from pushing premium gasoline into your engine. And now, watch how many places this exact thinking quietly shows up in things you encounter every week. Every single time you fill your car with gas, a compartmented tanker made that possible. It delivered the fuel in the first place. On the juice aisle at your grocery store, different brands and flavors sometimes share a single divided food-grade tanker on the same delivery route, each variety sealed in its own section. Airport fuel trucks are among the most heavily compartmented vehicles operating anywhere, tightly regulated and inspected constantly, because one surge event near a loaded commercial jet is simply unthinkable. Agricultural chemical trucks use compartments to keep substances that violently react with each other from ever touching in transit. The compartment there isn't just practical, it's what prevents a chemical disaster on a country road. Wine and olive oil transport across Europe uses divided stainless steel tanks to protect individual batches and grape varieties from cross-contamination, because a mixed batch loses its certification and its value entirely. On hazmat trucks, the ones marked with diamond warning placards are legally required by federal regulation to use specific compartment configurations depending on the exact class of material being carried. Military fuel convoys use compartments as a tactical decision, not just a logistical one. If one section of a tanker is damaged or punctured, the rest of the load survives and the mission continues. Industrial lubricant trucks carry different oil viscosities, different thicknesses, essentially in separate chambers, so they arrive at the factory or the workshop exactly as specified, not blended into something useless. Tanker ships carrying liquefied natural gas use compartmentalized hull sections for the same surge and safety reasons as road tankers, just at a scale involving millions of gallons instead of thousands. And water tankers operating in drought regions or disaster zones use compartments to serve multiple neighborhoods or relief sites with different water grades in a single trip, without cross-contaminating treated water with untreated water. You probably pictured a gas station receiving 4 separate truck deliveries for 4 different fuel grades. It was one truck, one driver, one trip, 4 compartments unloading into 4 underground tanks simultaneously. Here's the honest part. 1 compartments reduce surge. They don't eliminate it. A truck with 5 compartments that are all only partially filled still has liquid surge happening in every single one of them. A driver who loads unevenly or leaves one section nearly empty at highway speed is still carrying real risk. More compartments also means more seals, more valves, more connection points, and more things that can fail during loading or unloading. Valve failures have caused cross-contamination. Diesel has ended up in premium gasoline tanks at real gas stations. These events are uncommon but documented. The system is genuinely smart, but it only performs as well as the people running it. The driver, the loading crew, the maintenance schedule, the inspection process. No engineering solution runs itself. Compartments exist because liquid in motion fights back, and because a century of hard crashes produced a metal wall as the answer. What looks like a simple design detail is actually physics, history, and hard-won engineering, all welded together and rolling past you at 70 miles an hour.